Mathematical models, building functions. So one of the biggest things that I get asked all the time with teaching mathematics is, why do I need to know this? When am I ever going to use this? People are looking for applications. They're looking for, why do we actually learn any of this stuff? And sometimes I have to be entirely honest with people and say, you know what? You're probably never going to use this topic. Other times I'm perfectly honest and I tell you, look, you're going to use this all the time. So in chapter 2, section 6, mathematical models, building functions, this is where we're going to deal with some applications. How is this used, and trying it on some problems. So here we go. Boxes without topses. An open box with a square base is to be made from a square piece of cardboard 16 inches on a side by cutting out a square from each corner and turning up the sides. Express the volume V of the box as a function of the length x of the side of the square cut from each corner. Find the volume if a 2-inch square is cut out. Now, this is actually a very reasonable application. It's used all the time. If you've ever opened up a puzzle box, or you've opened up, a board game, any sort of boxes that you have a top that comes off, or an open box that does not have tops on it, you see that this is really what they've done a lot of times is they've got a certain size piece of cardboard and they're cutting pieces out of the corner so that they'll fold up and you'll be able to form the box. And there are actually people who go and get degrees in packaging, and they have to understand how that works. And we get into optimizing packaging because they want to get the most volume for the least amount of money, or they want to be able to have it look good, but still be cost effective for them to produce. So with this is a real life problem. So let's go and look about what's going on with this. So first of all, we've got this square of cardboard, 16 inches by 16 inches. We're going to cut squares out of the corners, and X is going to be the length of a side of those squares that we cut out of the corners. So if we want to find the volume of the box that's created, we're going to remember, volume of a box is length times width times height. In this case, the length is 16 minus 2x, right? Because we're going to cut out that corner that has a length of x. So 16 minus 2x, since it's a square, then we're going to square that. So 16 minus 2x, the quantity squared, and we're going to multiply by the height, which is x, the length of a side of that square that we're cutting out. When we simplify that equation, the 16 minus 2x squared times x, we get the volume as a function of x is 4x times 8 minus x squared. So that's our simplified form. So now we can deal with the volume. Now, the next thing the question asked was, what if you make x equal to 2? What is the volume of that box? So we're just going to take v of 2. We plug it into the equation. So 4 times 2 times 8 minus 2 squared, which gives us 8 times 6 squared, or the volume if x is equal to 2 is 288 cubic inches. So really not too bad. Now, I do suggest when you're dealing with applications, it's always a good idea to draw pictures. You may not like doing that. You may not feel that you need to do that, but it really does help to be able to visualize and keep yourself from making mistakes. For instance, excuse me, in this one, it would be very easy for you to put x in the wrong location, maybe count x as being the distance of it, the length of a side of the box once you've cut out the little squares, as opposed to counting them as the length of a side of the squares we cut out. Also, it'd be very easy to do only 16 minus x when it's 16 minus 2x. So drawing pictures is always a good idea, and it helps a lot. Is that my rectangle? A rectangle has one corner on the graph of y equals 9 minus x squared, another at the origin, a third on the positive y-axis, and the fourth on the positive x-axis. So we're making a rectangle. One corner is going to be on the graph of that parabola. Another is going to be at the origin. Third one, it just says, is going to be on the y-axis, the fourth on the x-axis. So basically, we're creating a rectangle which two of the sides are on the axes, and we're just adjusting the point of that other corner. We want to express the area A as a function of x. We want to know for what value of x is A the largest, and find the domain of A. Okay, so let's take a look at it. Again, draw things out. So I've got my axes here, and I've got a parabola y equals 9 minus x squared. So you can see my parabola there. And I've got a point on the parabola. Well, that point is going to define the corner of my rectangle. So we see that one side of the rectangle is the y-axis, one side is the x-axis. The other two sides are formed vertically and horizontally from the x and y axes respectively. So I can say that one side of this box has a length x, the other side of the box has a length y, where y is equal to 9 minus x squared. So I've now been able to put this together a little bit. So we want to find the area of the rectangle. Well, we know that the area of a rectangle is length times width. In this case, we have a length of x and a width of y minus x squared. So multiplying together, we get x times 9 minus x squared. If I simplify that, the area in terms of x is 9x minus x cubed. So there we go. So now we found an area. Then we want to know, well, when is that area going to be maximized? Now, this is something that you look at, and some of you may automatically be thinking, well, when x is equal to y, right? Because we know that a square will give you the largest area. But keep in mind, a square gives you the largest area when you have a fixed perimeter. We don't have a fixed perimeter with this. We're working along a parabola. So x equal to y does not give us the maximum area. So how can we find that? Well, the first method, and unfortunately not one that's available to you, is use calculus. This is a pre-calculus course, so obviously we're not using calculus. But if we use calculus, and it's relatively simple to do using calculus, we find that a of x is largest when x is equal to the square root of 3. And like I said, that comes out really easily in calculus. But we don't have calculus. So what do we have available to us? We have technology. So using technology, I can graph y equals 9 minus x squared, but that's great. I'd still have to work my way through a whole bunch of things. Well, you can also tell your technology to find the maximum value of that function. If you have a graphing calculator, you can have it find the maximum value of a function that you enter. I use Desmos, and using Desmos, I found that a of x is largest when x is approximately equal to 1.732, which is approximately the square root of 3. So using technology, we can do this. Otherwise, we really don't have a way. You could do trial and error, but you'd be at that forever. So either calculus or technology, that's how we can do this. The final question was finding the domain. The domain is the input. So basically, over what domain can we have x? Well, we're dealing with a rectangle, and we have two sides on the x-axis and the y-axis. So obviously x, which has to be a positive value because you can't have a length of a side that's negative, it cannot be 0, because if the length of a side is 0, we don't have a rectangle, we just have a line. So it can't be 0, so it's got to be greater than 0. It obviously can't be negative because you can't have a negative length. But how long can it be? How long can x be? Well, for that, we simply have to look at this parabola and say, well, when y is equal to 0, what's x? This is as far out as it can go. So we just find that out by setting the function equal to 0. So 9 minus x squared is equal to 0, x squared is equal to 9, x is equal to 3. Again, we can't let x equal 3, because if we did, then y would be equal to 0 and you would not have a rectangle. So now we can say that the domain would be from 0 to 3 exclusive. So that's about my rectangle. Why so distant? Let p equal xy be a point on the graph of y equals x squared minus 25. First, we want to express the distance d from p to the point on 1, 0 as a function of x. And 2, what is d if x is equal to 2? So first, we're going to come up with some function, d of x, which expresses the distance from d to this point, 1, 0, as a function of x. Then we're going to plug in x equal to 2 and see what the distance is. So again, drawing it out is a good idea. So let's put some axes on here. Let's plot that function. So we have y equals x squared minus 25. Put the point, 1, 0, right? We're getting the distance from that point to any point on this parabola. So let's put a point on the parabola. There's P, and we want to find D, the distance between those 2 points. So we're going to start creating a function for that distance. So first of all, we know we have 2 points. We have the point 1, 0, and then we have another point when the input is x, the output is x squared minus 25. So xy. So we have 2 points. Whenever you want to find the distance between 2 points, use the Pythagorean theorem. D is equal to the square root of the change in x squared plus the change in y squared, right? So that's what we're going to do. We're going to say d of x is equal to the square root of, well, we have x to 1, so x minus 1 squared, and y is x squared minus 25 minus 0, the quantity squared. So we just plugged in our x value, the difference of our x values, x minus 1, x squared minus 25 minus 0. And now we're going to go through and do the work. So multiply through, simplify, and I end up with d of x is equal to the square root of x to the 4th minus 49x squared minus 2x plus 626, which is not a pretty function, but it will give us what we need. So there's our function of distance in terms of x. Now we want to say, well, what happens if we set x equal to 2? What is the distance between the point on the parabola and the point 1, 0? So we make d of 2, substitute in 2 everywhere we had an x, giving us the square root of 2 to the 4th minus 49 times 2 to the squared minus 2 times 2 plus 626, which after we go through those simple multiplications and the square root, we find out that the distance is approximately 21. Now notice I didn't put inches or anything else because we never said what the units were. So my distance is just approximately 21. So as we saw from this, we can use these mathematical functions that we're coming up with to answer questions about things in the real world. Now you may look at that and go, well, wait a second. I mean, why so distant? What does this have to do with the real world? Well, it actually can mean a lot, because what if you're trying to create a parabola and you want to get a distance from a certain spot on the parabola so you know what's happening? And this happens. If you've ever seen a satellite dish is a parabola. There are parabolas everywhere in the world. So having to do some calculation like this is not rare at all. It's actually quite common. And as we saw with the boxes, that's something you deal with every day. You see boxes and you go, well, how did they come up with this? Someone just kind of cut the box into a certain shape and try and see if it fit or not. Well, that's how they used to do it. But now we use calculus and we use other tools to be able to determine what size to make those containers. So welcome to the world of applications of mathematics.